Okay, let's take a look at the Hall effect sensor. Let's look at the internals a little bit. I always look that if you're going to work on something, you're going to work on a system. Let's say you come to a system you don't have you don't know anything about, okay? Now, you're going to take something that's broke and you're going to put it back into a working condition for something you don't know how it works to start with. I mean, so what are you left with? Basically, you're going to be changing parts. You'll take an educated guess, let's change this, and that don't work, you change this, change that. And you know, you see in forums where people change all these sensors and it still doesn't work, and then they want to know what to do next. And I'm a firm believer. I teach maintenance and electrical techs. You know, a lot of the guys that get in the habit of changing parts, they're not familiar with the system. So I'll go through the training, teach them how a system works. And in fact, one guy I've been working with all this week, I mean, he's really getting excited now because he understands the system. He's not afraid to go to some equipment now to work on it, you know, because he understands now how the system works, what does what, and he knows how to check it now. So I figured, you know, this might be more than you ever want to know about Hall effect sensors, but I'll give you all the info I know about them, and then this way, the more you know, you can take and add, you know, to your knowledge of them. And also in the process, one other thing is that the more you guys know about this system and how it works, you guys can help me diagnose right along with me. So you'll know what I know, so you can put together your own thoughts about what you might think it might be. Okay? All right, so let's get started on this here Hall sensor. All right, being a Hall sensor, it's an active device. That means that with electronics being inside this device, you got to have a source of power. You got to have a positive, you got to have a negative powered up, like any electronics. Okay, so we're going to put a sensor ground down there. It's got to have a ground. Now, by the way, this is all being provided up here by the ICM, that's ignition control module. So that's where the supply volts are coming from to supply the power for this here Hall effect sensor. Alright, so now we're going to have a B plus voltage, ignition voltage, okay, and that's going to come down. Now, one other thing, here's something about service manuals. You read one part, it says one thing, you look at another part, it says something else. Now, over on the ICM side where it supplies the power, it says ignition voltage, right? So it'll be like this. Okay, so that's 12 volts, and I guess if you crank the car up, then it'll go to, you know, your charging voltage, 13.5 or whatever. But then I looked on the other side where the crank sensor is at, and that says 10 volt reference. Like 10 volts is maybe coming out of the ICM. So I did a little test there, and what I found out was that when you turn the switch to the on position, I actually had 10.5 volts here. That's with the switch on. So then I cranked the car up and I had 13.5 volts. And I said, well, isn't that interesting? Then I turned the switch off, still monitoring that voltage, and the voltage dropped down. You know, I turned it off and then turned it back on, and then the voltage actually was dropping down, and it came back down to 10.5 volts. So I'm going to call this voltage right here for the supply volts. I'm going to say anywhere from 10.5 volts up to, let's say 13.5, your charging volts. Okay? Thought that was a little interesting. All right, so when it says 10 volt reference, it makes you think there's a regulator inside of the ICM. However, if there was, then of course that voltage should not vary when I crank the car up. So maybe there is not a regulator up inside the ICM. However, we definitely probably going to have one down inside this sensor, because we don't need the supply volts to be varying all up and down on the place, because the variation in the supply volts to the Hall chip in electronics is going to make a difference in what voltage is going to be coming out of the Hall effect to, and then that's going to upset everything else down the line there. So anyway, let's put in a voltage regulator here. I'm going to call him volts reg, okay? And there's our incoming volts coming into the regulator. Of course, we do need a ground, so let's connect him up. And now we're going to have an output volts coming out of it. Now, we don't know what internally is, but let's say it's 5 volts. That's pretty regular, common voltage for a regulator. Now, for the ones that's not familiar with a voltage regulator, it's usually it's a 3-terminal device. You have your incoming voltage, you have a ground connection, you have an output voltage. As this here supply volts was to vary, like I said, in say from 10.5 up to 13.5, then this here voltage is coming out of this regulator is going to be maintained at 5 volts. So it's not going to vary at all. Okay. Now, what we want to do is we want to take and put our Hall effect chip here. Okay. Now, being electronics, could be an N-type or P-type material here. We're not going to get into that. We'll save that for another day. Just a silicon chip in there, and we're going to put a supply volts to that. Okay. Now we're going to have the ground connection. We've got to power that up just like any electronics, and we're going to call this a Hall chip. Okay. Now, you remember on the side that we had the voltage being developed? So we're going to put that out here to the side. There's our Hall voltage. Remember, that's going to be developed in the presence of a magnetic field. When no magnetic field is there, we're not going to get any voltage out. Now I'm going to feed this to a differential amp. Okay. And what that's going to do is it's going to take the difference of the voltage here, it's going to amplify it, and it's going to give us an output over here. Okay. And let's go ahead and give him a supply volts there for the op amp. Alright, now let me just put him up here a little bit. Now we're going to take him and we're going to feed him to what's called a Schmitt Trigger. And we'll give him some supply volts. There's my negative down there, and there's my positive 5 volts up there on the top. Now, what does the Schmitt Trigger do? Okay, what does this here Schmitt Trigger do? The Schmitt Trigger has hysteresis built into it, and that's to, let me back up a little bit before we get there. Let me say everything is not perfect. Electronics is not perfect. It's not 100% perfect. Hall chip's not perfect. Ideally, what we want the Hall chip to be is there's no magnetic field there. We don't want it to produce a voltage, but it could produce a very, very small amount. But that small amount, we don't want to sit there and amplify it and then drive a transistor and turn it on when it's not really seeing that field. So the Schmitt Trigger has two levels of voltage. One is the upper voltage, one is the lower voltage. Okay. Now, this is also, you can use a window comparator. Take an op amp, wire it in a window comparator mode, and give you these here 2 thresholds of voltage. Okay. So basically, what it is kind of like anything that's in between here, in the voltage. Let's say the Hall effect voltage is in there that we don't want to be changing state. In other words, we have to go up above this. Let's say when we get above this level, we know we got a good threshold of voltage, a Hall voltage coming out, so now we can change state. So that's when the Schmitt Trigger is going to give us an output and say go high, or go rise to the supply volts. Okay, on the same token, let's say now we don't have any magnetic field, so now we know the voltage is going to drop, but we don't want nothing to happen until it gets below this threshold. Once it gets below that threshold, now that's when we want to activate the Schmitt Trigger to give us an output to turn on the transistor, or turn it off rather. So this part that's in here, upper level, lower level threshold voltages, this part in here is the hysteresis. So this is where the voltages, let's say, coming off of the Hall effect, we want to ignore for those, those little anomalies that I mentioned. Okay. Now let's get back here to our crank sensor here. Okay, so now the output of this here Schmitt Trigger is going to be driving, and look here, you already know this. This is the NPN transistor. Okay. There's our emitter, there's our base, and here is our collector. Now collector is going to go up here. And let's see, I'm going to put me a resistor there, and on this side of the resistor I'm going to put 6.5 volts DC. Now how do I know 6.5 volts DC is there? Because I measured it. Okay, so one of the anomalies out of the way. Okay, now let's see what is actually happening. Let me draw my ICM a little bit further over here. Okay, now this point right there where my dot is, right on this side of the resistor, is what the ICM is going to be looking at. Now that's going to be going to a counter. Okay, it's going to be counting these here pulses, these square wave pulses that's coming out. Okay, now let's see how this thing actually might work. Okay, so we have let's start off with let's let it see a magnet there. All right, so remember we have our window on our interrupter ring. There it is. The magnet can be seen, the magnetic field can be seen by the Hall chip. There produces a Hall voltage. So now we have voltage across the Hall chip. Okay, now that voltage is getting amplified. We take the difference of that voltage, subtract it, then we take a gain that's preset, we amplify that voltage, and we come over here. Now we want to make sure that that voltage is in that threshold that we wanted. If it's, let's assume it is, it's all been set, and resistor values have been set for everything for that threshold. Alright, so now that means that we want an output out here that's going to be high. Okay, so it's going to be high. So you remember the 2 volts that I mentioned? You got to have a positive volts out here to turn on the junction between the collector and the emitter. Remember this right out here? Just a switch. Let's think of it as a switch. Now, when this positive volts is here, let me put my plus 2 volts. That's going to turn on. Now we're going to go through. Now, imagine this is, if you want to think of that, there's our ground connection. Okay, so you can see the emitter goes to ground. Remember I told you if you see that, then this isn't a switch mode operation for this here output transistor. Now that ground is going to be sitting right up here. Now it's there. It's because the ground is just going to go right there. So now that means we're going to have 0 volts. Okay, so let's draw our 0 volts. We're going to draw this up as a little waveform. Okay, so there's our 0 volts. Now here comes the blade on the interrupter ring. It's going to block the magnetic field from the magnet. Okay, therefore we're not going to have any Hall voltage, nothing to amplify, 0 volts out here. So the Schmitt trigger is going to see that threshold that it's below where it needs to be, and then the output of the Schmitt trigger is going to go down to 0 volts. Now 0 volts on the base is going to make this here between the emitter and the collector open. So now we're open. Now with this here being open, our ground can't get up to here now because we got to open in here, right? So that means that our supply volts up here at 6.5 volts is going to rise at this point right here. So anywhere down this line is going to be 6.5 volts. Now the 6.5 volts is going to be seen, okay, by the counter. So now it goes up. So there's our 6.5 volts. But now remember, we have the blade that's blocking it. But the blade is going to be sitting there for a little bit of the width of that blade. So how long that is, that width of that blade, that's how long that is going to stay high, because it's blocking the magnet. Now here comes again. When it comes up again, the process repeats. We get our Hall voltage, gets amplified. Schmitt trigger turns the output on to the transistor. Transistor turns on. That's going to pull it back down to ground again. So here we go. Now this process is just going to repeat over and over. Okay. Now the counter up here is actually counting. It's counting it's either counting the rising edge or the falling edge of the pulse. I don't know which one it is. It doesn't matter. You'll still get the same value anyway. Well, let's say it's the negative. It's on the falling edge, which is falling. Okay. Now, by the way, for the ones that don't know what I'm talking about a rising edge and a falling edge, when the voltage goes from 0 volts and it's rising, going up, then this here is going to be the leading edge. That's the leading. Now it's going to stay on and now it's falling. This is the falling edge going down that way. So you're going from the supply volts back to 0. So this is called your falling. Sometimes, going back, sometimes you hear leading edge. It's also called a rising edge, okay? Now it's going to stay off for this length of time. We're at 0 volts. And by the way, when it failed, remember I said we're just counting on the falling edge, then the counter up here, it's made 1 count. So it knows it's made 1 pulse, basically. So now it comes across, it's off. Now it goes up, and now still nothing. Goes across, on, now it's falling. Okay, so now we just went to 2 counts. Now we went over, we're going up again on the rising edge, coming across, staying on, now we're falling, and now we've got 3 counts. So with 3 counts, it knows already, if this was that 3x signal, that it made 1 revolution. Alright, so we're going over the diagram. Now some of the terms you might hear is pull up, pull down. How about this one? Sinking, sourcing. Let's go over that a little bit, because you're going to run into some crank sensors, cam sensors, and it'd be pull up, pull down, sinking, sourcing. So let's clear that up. Let's go over that a little bit right now. Okay. And also in the process, we'll also be talking about, about the test light, how you can simulate that crank signal. Let's see how that actually works too. So I'm going to kind of put all this stuff together, cover the crank signal as much as we can. And then if you run into these terms, pull up, pull down, sinking, sourcing, then you'll know what that means. Okay, let's go over our transistor, okay? We have an NPN transistor. You've already seen this. The emitter is tied to ground. We know it's in a switch mode, right? And this is going to be in our crank sensor, all right? So, there's our crank sensor. Now, we're going to go up, right? And we're going to go up to here to our ICM. Now, I'm just drawing the signal here now. Okay? And then up here, I'll put my 6.5 volt DC. All right? All right. Now, remember, this is the part that's going to the counter. And I'm going to say, look here. All right. Okay. Now what this is called, this is our output signal going this direction. So this is an output, all right? But that means this up here in our ICM, this is an input. That makes sense. No problem so far, right? All right. Now this one down here is a sinking, okay? This is called a sinking output. Okay? Why is it called a sinking? Because the current is being sinking to ground. Think of sinking as going down. You know, you're out there in the ocean, you're in a boat, you're sinking. You're going to the bottom, right? Ground is at the bottom, 0 volts. That's why they call this a sinking. Because when it turns on, this is going to be a sinking output. Okay? On the other hand, let's look up here at the input. This is a sourcing input. Sourcing, going up to the top, rising. Here's our supply volts. Okay? All right, does that make sense? So if you got your positive volts here, it's the input. This is sourcing input because it's providing the voltage for this here transistor. On the other hand, this would be an output. It's pulling this to ground. Okay? All right? All right. Pull up, pull down. I look at that, it's the same thing. If you're pulling down, you're sinking. All right? You're down, okay? You're going down, sinking. Same thing. When this transistor turns on, you're pulling it to ground, all right? The ground is up here. Right there where it says look here, it goes to ground. So you can consider this here transistor to be a pull down design. Okay? All right? Now let's look at another one. Now, another one is where we have a PNP transistor. Now, I haven't talked to you about PNP transistors, but it's no different from the NPN other than the polarities are reversed. All right. Remember over here, the NPN takes 2 volts to turn it on. Well, the PNP, I put 0 volts on it, and it turns the transistor on exactly backwards. Okay. The polarities on the collector and the emitter are backwards. You notice how the emitter right here goes to 0 volts? You notice how the collector goes to a supply volts of being positive? Well, on a PNP transistor, those polarities are also reversed. So let's take a look and let's see how that might work, okay? Because some crank sensors you may run into this type of design. Here's my transistor, there's my base. Now when the polarities are reversed, and usually you put your supply volts on the top. So that means that the emitter, right, will go on the top. The collector, okay, will go down here. And what I'm going to do is I'm going to shoot him back up this way, okay. Now, my plus V, my B plus, is going to be provided on the emitter right here. Notice the difference right there. Now, what they could do is, of course, if I have my ICM up here and I'm supplying my B plus voltage, then I'll go down, and then what I can do is I'll just connect it like that, okay? But you see the difference between the two? These two right here? By the way, an NPN, you can recognize whether it's NPN or PNP by which way the arrow goes. So the arrow points out on the NPN. And what the arrow is telling you is the direction of conventional current flow. Where on the other hand, the PNP, the arrow points in. And that's also conventional current flow. That's the direction it's going to go. Okay? Now, when we get back up to the ICM up here, then we're still going to have our load resistor, but now it's going to go to ground. Okay? And we're still going to look at this same point on the other side of the resistor. Okay? So, how does this one work? It works no different than the other one. If you look right here at the transistor, right? If I put 0 volts, on this base, there's my switch, still the same between the emitter and the collector. Now, my voltage is coming down, positive volts. It's coming down, coming down, coming down, going back up, right? Now, let's say I have 12 volts. I got 12 volts up here, all right? That's with the transistor turned on, yet I'm putting 0 volts now on the base. Remember, everything is backwards. Now let's go the other way. Let's say I put my 2 volts on here. Now my transistor is turned off. Okay, so here's my voltage sitting right there, open between here, right? So what is right here? My ground is going to come right down to here. And that's going to put it back to 0 volts. So everything's the same, it just works backwards, okay? Now, this part down here, all right, you see how we are sourcing voltage now? On this one, it's called sourcing, okay? This is a sourcing output. This one up here is a sinking. See how the ground up here? This is a sinking input, okay? Now, as far as in the respect of what a pull up, pull down, this one here is a pull up, okay? Where this one over here was a pull down, okay? Because we're pulling it. Look, the way you can keep up with it, what does the transistor do? It's pulling it to ground, right? And this one here, when it turns on, what does it do? it is pulling, it is taking the source voltage and rising it up. See when it turns on? See how the voltage goes up? So it goes to 12 volts. Okay, now let's look at it with a, let's look at it like with a test light. Okay, so we know this is the NPN, so we know our voltage is coming up from here. Okay, so there's our plus, say 6.5 volts, right? Okay, let's do it right there. All right, so you know a lot of you guys have seen Paul data with scanner data, you know, with the test light. So if you can see the circuit of what's happening, I think that's a little bit more interesting to know what, I mean, you can remember this, if you see the voltage, you know, pull up, pull down, all this other stuff, but look what we got. When we disconnect this here connector, this is isolated, right? So now this is out of the circuit, right? But what do we need to do here? We need to pull this to ground, don't we? So here's our test light. There's our test light. So we're going to pull, what does he want? What does this want? It wants a ground. So we tie it to DC negative on the battery post. Now we're going to touch right there. See? Now when you have this here out and you check your voltage, what are you going to get? You're going to get 6.5 volts, right? Because there's no current flow. It's an open circuit. So what you're going to do, you're going to do the same thing the test light is doing that the transistor is doing. You're going to pull it down to ground. So there's your ground right there. So when you pull it to ground, what's going to happen? And remember, it's going to look right here. Okay? So when you pull it to ground, there's our 0 volts. Now, you take the test light off, what's going to happen here? The 6.5 volts is going to be sitting right there then, because it's going to be 6.5 volts on this side. So there it goes up. Pull it back to ground, touch it again, right? And it'll go across, and then you touch it again, down it goes, okay? And you'll just repeat that process every time you touch it off and on, all right? And it's the same thing with the PNP, except you want to take him, all right? Let's go back, let's get our little diagram. Look up here in ICM. You can see it very clear, right? Here's our resistor. Remember, now he goes to ground. So, here's our transistor down here, but remember, he's out of the circuit. Okay, so if you take your voltmeter and you measure right there, what are you going to get? Right? You're going to get 0 volts. So let's put our test light in there. What do we need to do? We need to pull him up. So we're going to put a voltage and we're going to connect this to B plus, 12 volts positive. Now we're going to take and put our test light right there. And remember, there's our point right out there that it's looking at. Right, look here. So when you put your 12 volts and you put it on this side of the resistor, what are you going to get? You're going to get 12 volts. There's our 12 volts. Then when you take it off, what's it going to do? Then your ground's going to be sitting right there. So now it's going to go down. And then that process will repeat over and over. Okay guys, that's going to wrap up this here crank sensor. Hope you guys understood that. If you don't, I'm sure you'll ask me some questions. Hopefully it wasn't too detailed, but I always look, the more detail, more information you got, it's got to help you in troubleshooting. So you guys take care, and I appreciate you guys watching the video.